For generations, standard science textbooks provided a comfortable, self-contained map of our planetary neighborhood. They drew the boundary line neatly at Pluto's orbit, creating the distinct impression that a clean, empty void stretches all the way to the next star. But the reality is far more chaotic. Past the outermost planets lies an empire of magnetic shields, supersonic stellar winds, and highly radioactive space. Clinging to that classical textbook model obscures the actual physical reality of our cosmic neighborhood. Our planetary network is a quiet harbor, surrounded by a massive, highly active weather system of plasma. Our sun is a tempestuous nuclear furnace. It continuously blasts out a torrent of highly charged plasma, known as the solar wind, accelerating outward at roughly 1 million miles per hour to inflate a massive protective magnetic bubble called the heliosphere. This diagram shows the architecture of that bubble. At roughly 94 astronomical units away from the sun, this supersonic wind crashes into the cold, dense pressure of the galaxy itself. The solar wind drops to a sluggish crawl, creating a compressed, chaotic borderland known as the termination shock. Pushing further out to roughly 121 astronomical units, we find the absolute outer membrane of our solar system's magnetic defense, the heliopause. For decades, scientists like astrophysicist Carl Sagan debated exactly what happens at this cosmic border. Some hypothesized a gradual transition into the galactic medium, while others predicted a sudden drop-off into darkness. Pinpointing the exact nature of this boundary is critical. This magnetic cocoon deflects roughly 70% of the lethal, high-energy cosmic radiation tearing through deep space, shielding Earth from total sterilization. In 1977, NASA launched Voyager 1 and its twin, Voyager 2. These remain the only human-made objects ever to successfully breach the heliopause and physically sample the space outside. This graph illustrates the exact moment of crossing. Voyager's onboard instruments recorded a sudden 10-fold spike in the density of cold, highly radioactive galactic matter as the warm particles of our sun vanished. Operating decades past its prime, Voyager 1 suffered a catastrophic flight data system glitch in late 2023. Communicating across a vast expanse that requires over 23 hours for a signal to travel one way, NASA engineers successfully relocated and recompiled the broken code remotely in 2024. By restoring that data transmission, Voyager continues to act as our only live sensor in the dark, proving that interstellar space is a pressurized ocean of plasma left behind by ancient supernovas. Yet, despite crossing into interstellar space, Voyager has not escaped the solar system. It remains entirely bound by the gravitational pull of our sun. This diagram compares the scale of our magnetic bubble to the true boundary of the sun's gravity. A spacecraft must cross the Oort Cloud, a colossal spherical shell of icy planetesimals that begins 2,000 astronomical units away and stretches to a staggering 200,000 astronomical units. We cannot directly image this dark, icy vault. However, the dwarf planet Sedna follows a wildly eccentric 11,000-year orbit that drags it out to nearly 1,000 astronomical units, providing empirical evidence of the cloud's inner architecture. Moving at nearly 1 million miles a day, it will take Voyager 1 another 300 years to reach the inner edge of this cloud, and 30,000 years to fly out the other side. The gravitational reach of this icy shell effectively determines the true boundary of our star system, extending far beyond the orbits of the familiar planets. Theoretical physicist Freeman Dyson calculated that this dark expanse is exceptionally rich in critical elements, including water ice, carbon, and nitrogen. He hypothesized the feasibility of genetically engineering plant life to grow directly on these comets. By trapping passing sunlight through organic mirrors to generate micro-greenhouses, these Dyson trees could turn the outer void into stepping stones for deep space migration. But this reservoir of resources is also highly unstable. The mass of the Milky Way's core pulls on the outer fringes of the Oort Cloud, generating galactic disk tides that routinely knock billions of comets loose and pull them into the inner solar system. This tidal force creates a multi-million-year cycle of comet displacement, making the Oort Cloud both a potential bridge for migration and a primary driver of historical mass extinction events. Once you cross the outer threshold of the Oort Cloud, you enter the true interstellar void. Our entire solar system is traveling through the local interstellar cloud, a warm, low-density expanse of hydrogen and helium gas spanning roughly 30 light-years across. This diagram illustrates what our modern space telescopes are finding in this expanse. Data from exotic star systems like LHS 1903 reveal inside-out planetary configurations, where massive gas giants press directly against their host star, while rocky planets orbit on the freezing outer rim. Discoveries from thousands of cataloged systems show a universe of wildly diverse architectures. This evidence suggests that our specific layout, with rocky worlds clustered near the star and gas giants far out, may be a cosmic outlier rather than the rule. The perceived edge of our planetary system is an active landscape of magnetic frontiers and trillions of pristine ice worlds. As our technology advances, upcoming space observatories will soon be able to map the dark architecture of this extended interstellar backyard with extreme precision. We have been looking at an unmapped ocean for centuries, and we are finally learning how to sail.